In this episode, we start to get a little bit closer to a full buffer overflow. In the last episode, we have learned how a buffer overflow can change local variables, which are stored on a stack. Now we will have a look at stack level 3, which is very similar. If you forgot how we were able to solve stack level 0, you should go back and watch it again. When we look at this code, we see that it's basically the same. The only difference is the name. Instead of a modified variable, we have the fp variable, which is defined as a function pointer. The syntax looks a little bit ugly, but if you check the if case, it simply checks if fp is not 0 and then just calls fp, as if it were a function. Now you know that a function has an address location in memory, so it will basically call whatever address is stored in fp. Now like the modified variable in stack 0, the function pointer fp gets set to 0, and after the gets function, it will be checked if it's not 0 anymore. So we know that fp must also be stored on the stack. As a hint, it says that we can use GDB or object dump to determine where the win function lies in memory. So let's first use GDB, and you can use examine or print to get the address of win. Then set the disassembly flavor to intel and disassemble main. Exactly like stack 0, we can see that it makes space for hex 60 bytes on the stack. Then we set ESP offset 5c to 0, so that is the location of the fp variable. After the gets, we compare this value if it's still 0, and that if that were not the case, we load the value into EAX down here and call that address. So let's set a breakpoint at this call. Now execute it and enter enough characters to overwrite this value on the stack, exactly like last video. Okay, we hit the breakpoint. Let's look at the registers, and we can see that we have successfully set EAX2 for 14144141, which is the ASCII value of a capital A. And the next instruction tries to call this address, so basically jump there. But that is obviously invalid memory, so we get a segmentation fault. Now open a second SSH session and create a Python script that will be our exploit. So let's first try to figure out which offset controls EAX. So simply print a recognizable pattern, for example the alphabet. Okay, cool. So pipe this output in a file. Now you can use this file in GDB as input, so we don't have to type it every time. It will use the content of the file as input. Now run and use the arrow left to redirect the file content in the standard input of the program. Okay, so EAX is hex 451, and that is capital Q. So now we know which offset modifies EAX. Let's rewrite the code a little bit. Let's call this part up to the queue's padding. So we want to write here the address of the win function. So simply use \x as hex escape for those byte values. Oh, oops, that doesn't fit. There is a leading 0 missing. Save, write the file, and check it in GDB. Huh? The address looks a bit weird. Looks like the wrong way around. Well, that is because of the endianness. So the numerical value will be basically the other way around. Cool, EAX looks fine now. Let's continue, and we get code flow successfully changed.
Hack the planet! Hack the planet!
Now let's quickly solve the next level as well. This level is our first buffer overflow where we take advantage of the stack layout. The code doesn't contain much. There is no function pointer variable we could overwrite and no modified variable. But it still wants us to execute win. So how do we do that? Now, do you remember how the stack layout looks from last video? Here's a quick recap. So here on the left you can see the assembler code. And on the right I will illustrate the stack with the 3 important registers: the instruction pointer EIP, the stack pointer ESP, and the base pointer EBP. So first it starts somewhere else with call main. Call will push the theoretically next instruction pointer onto the stack and then jump to our main function. As you can see, when the address of the next instruction was pushed, the stack pointer got incremented and the address is placed there. So now comes our push EBP. How do we know now where to return to from main? Well, if you remember, call pushed the address of the instruction after the call. So the next value on the stack is where you want to return to. And the red instruction is basically just popping this address into the instruction pointer, and thus jumping back where we came from. So as you can see, when a function is called, the address where we want to return to will be stored on the stack. So instead of overflowing a local variable, we can simply overflow the return pointer on the stack. And when main would return, it would read the wrong value and jump there instead. So let's use the code that we have just written and modify it a bit. Let's make the payload a bit longer and simply throw it at this program in GDB. Segmentation fault in hex 5.4. So we successfully redirected code execution to bad memory. And if you look closely, you can also spot that the base pointer is hex 5.3. So that one was also written. Because if you remember from last video, the old base pointer is also stored on the stack, right before the instruction pointer. And hex 5.4 is t. So t allows us to control the instruction pointer. This time let's use object dump to find the address of the win function. With -t we get all symbols, and then we can grab for win. So there's our address. Let's remove everything up to the s, because that is the base pointer. Now we create two variables, EBP and EIP. We don't care about EBP, so we can just set it to whatever we want. And next we want to set the instruction pointer. But let me show a better way to encode the address as a string. So import struct, and then you can use struct.pack to convert the address from the integer number into a binary string. Then print the padding and append EBP and EIP variable. So let's execute this exploit and pipe it into stack level 4. Code flow was successfully changed. Amazing! We smashed the stack and controlled the instruction pointer. But you still get segmentation fault? The reason for that is that after the win function is complete, it tries to return to the next value on the stack, which is now some gibberish and likely not valid code area. So it will crash eventually. But we don't care, because we executed what we wanted. In the next video, we will write our first buffer overflow with shellcode, which will show you how powerful a buffer overflow can be, and it will be our first exploit that will get us root privileges.